Let's see energy band in semiconductor. In semiconductor, we have mainly two bands. One is conduction band at higher energy state, and another is valence band, which is at lower energy state. This one is conduction band, and the state with lower energy is the valence band. The lowest energy of conduction band is denoted by EC, and highest energy of valence band is denoted by EV. And the gap between conduction band and the valence band is forbidden energy gap. Electron energy increases in this direction. Now, at room temperature, at absolute temperature, absolute temperature means temperature is minus 273 degrees centigrade, or temperature is 0 Kelvin. At absolute temperature, valence band is completely filled, full of valence electrons, and conduction band is totally empty. These are the valence electrons, and conduction band is empty. Now we have the expression for forbidden energy gap. For silicon, it is 1.21 minus 3.6 into 10 to the power minus 40 electron volts, and for germanium, energy gap is 0.785 minus 2.23 into 10 to the power minus 4t electron volts, where this temperature T is temperature in Kelvin. Now let us see what is Fermi-Dirac function. Expression for Fermi-Dirac function is Fe, that is equal to 1 upon 1 plus e to the power e minus ef by kt. This Fe gives the probability that energy level E is occupied by electron, and Fe, in fact EF, is called Fermi energy level. Fermi energy level. K is Boltzmann constant, T is temperature in Kelvin, and the value of this Fermi-Dirac function at Fermi energy level is 1 upon 1 plus e to the power 0. which is 1 by 2. It means probability that energy level EF is occupied by electrons is 50%. Now we can draw the Fermi-Dirac function versus E curve. But before that, let us see the value of Fermi-Dirac function at absolute temperature. At T 0 Kelvin, and if energy is greater than Fermi energy level, in that case the Fermi-Dirac function is 1 upon 1 plus e to the power. See, if E is greater than EF, then E minus EF is positive and temperature is 0. So it is e to the power plus infinite, and e to the power plus infinite is infinite. So this is 1 upon 1 plus infinite, or 1 by infinite is 0. So at absolute temperature, if energy is greater than Fermi energy level, then probability or Fermi-Dirac function is 0. Similarly, if E is less than EF, energy is less than Fermi energy level, then Fermi-Dirac function is 1 upon 1 plus. If E is less than EF, then this difference E minus EF is negative. So Fermi-Dirac function is 1 upon 1 plus e to the power minus infinite now, because E minus EF is negative and e to the power minus infinite is 0. So it is 1 upon 1 plus 0, or 1. So if E is less than Fermi energy level, then value of Fermi-Dirac function is 1. Now we can draw the Fermi-Dirac function versus E curve. As I said earlier, this Fe gives the probability. So obviously it has values between 0 and 1. And this is horizontal axis is E. Somewhere here we have EF. Now we have two portions. First portion is portion where E is greater than EF, and second portion where E is less than EF. So if energy is less than EF, then Fermi-Dirac function is 1, and if energy is greater than EF, then Fermi-Dirac function is 0. So this is the Fermi-Dirac function at absolute temperature. Now if we increase the temperature, then the curve goes like this. At Fermi energy level, the value of Fermi-Dirac function is 1 by 2 at any temperature. Suppose temperature here is T1. Now if we further increase the temperature, then curve goes like this. Again at Fermi level, Fermi-Dirac function is 1 by 2. This curve is for temperature T2. Every time at any temperature, value of Fermi-Dirac function at Fermi energy level is 1 by 2. Here temperature T2 is greater than T1, and that is greater than absolute temperature. We will use this curve in further analysis of semiconductor. Now let us see the concentration of electrons. Concentration of electrons in conduction band of semiconductor. Concentration of electrons in conduction band. Del N is rho E del E. Del N is the elemental concentration of electron at energy level del E, and rho E is the density of electrons. Density of electrons in energy interval del E. This rho E is given by GCE into Fe. This GCE is called density of state. Density of, in fact, allowable states in conduction band. And this density of state is given by gamma E minus EC to the power 1 by 2, and in conduction band E is obviously greater than EC because EC is the lowest energy of conduction band, and this gamma is basically constant. The gamma is 4 pi m h cube 2m to the power 3 by 2, where m is mass of electrons and h is the Planck constant. So Fe is again Fermi Dirac function. Fe is 1 upon 1 plus e to the power E minus EF by kT. Now in conduction band, E is greater than EF. So the value of e to the power E minus EF by kT is large as compared to 1. So we can rewrite the expression for Fermi Dirac function as 1 upon e to the power E minus EF by kT, or this is simply e to the power minus E minus EF by kT. Now substituting the value of rho E, or substituting the expressions of GCE and Fe in first expression. Now del E is gamma E minus EC to the power 1 by 2, and Fe is e to the power minus E minus EF by kT. Del E is also there. So now the concentration of electrons in conduction band can be obtained by integrating the above expression from EC to infinite, because EC is the lowest energy of conduction band. This is del N. N is integration of gamma E minus EC to the power 1 by 2 e to the power E minus EF by kT from EC to infinite. Now let us assume that E minus EC by kT is x. So del E is kT dx. So the expression for n becomes integration of gamma kTx to the power 1 by 2. Now replacing E by kT with x plus EC by kT. E is replaced by x plus EC by kT. Here we have minus EF by kT, and del E is replaced by kT dx. Now the lower limit of integration is 0, and the upper limit of integration, if E is infinite, then x is also infinite. Now we will integrate this. This is here, see, here gamma is constant, and kT to the power 3 by 2 is also constant, and e to the power minus EC minus EF by kT is also independent of integration. So we'll have to integrate x to the power 1 by 2 e to the power minus x with respect to x. And the integration of this term is root pi by 2. So the expression for concentration of electrons in conduction band is gamma kT to the power 3 by 2 excuse me, e to the power minus EC minus EF by kT root pi by 2. Now this gamma kt to the power 3 by 2 into root pi by 2 is constant, and it is denoted by nc. So the expression for n is nc e to the power ec minus ef by kt, where nc is gamma kt to the power 3 by 2 root pi by 2. It is called effective density of states in conduction band. Similarly, we can derive the expression for concentration of holes in the valence band. Now let us see concentration of holes in valence band. Del P is rho E del E. Now again rho E is density of state in valence band, and it is given by JVE into 1 minus Fe, where Fe is Fermi Dirac function, and 1 minus Fe gives the probability of finding of holes in the valence band, or 1 minus Fe gives the probability that energy level E is occupied by holes. And the expression for this GV is rho is density of holes in valence band for energy level del E. GV is density of state in valence band. Density of states in valence band, and rho E is density of holes in energy interval del E. 1 minus Fe gives the probability that energy level E is occupied by holes in valence band. Now the expression for this GVE is gamma. Gamma is again constant. Gamma EV minus E to the power 1 by 2, where E is less than EV, because EV is the highest energy of valence band. So E has to be less than EV. Now 1 minus Fe is 1 minus 1 upon 1 plus e to the power E minus EF by kT. So 1 minus Fe is e to the power e to the power e minus Ef by kT divided by 1 plus e to the power e minus Ef by kT. Now in valence band, this E is very small as compared to Ef. So e to the power e minus Ef by kT is very small as compared to 1. So the expression for 1 minus Fe in valence band is 1 minus Fe can be approximated as e to the power e minus Ef by kT. So now substituting the expression for GVE and 1 minus Fe in the expression of dP. This is GVE 1 minus Fe dE. So this dP is gamma EV minus E to the power 1 by 2 e to the power E minus Ef by kT dE. Now the expression for concentration of holes in valence band can be obtained by integrating this dP from minus infinity to EV, because EV is the highest energy of valence band. So P is integration of gamma EV minus E to the power 1 by 2 e to the power E minus Ef by kT dE. Here gamma is constant. Now substituting EV minus E by kT by x. So this dE is minus kT dx. So the expression for P is now, see, if E is minus infinite, then x is plus infinite. Okay, plus infinite. And if E is EV, then x is 0. Minus infinite to EV, EV minus E. If x is if E is minus infinite, okay, then x is plus, okay. Now gamma EV minus E means kT x to the power 1 by 2 e to the power E by kT is replaced by E by kT is replaced by EV by KT minus X. Here we have EF by KT, and D is replaced by minus KT dx. Because of this minus sign, we can interchange the limits. Here gamma is constant, so it will come out. Gamma is independent of X, so it will come outside the integration, and KT to the power 3 by 2 and E to the power, see, we can write this expression as minus EF minus of EF minus EV divided by KT. This term is also independent of X. Because of minus sign, we are interchanging the limits. So again we have to integrate X to the power 1 by 2 into E to the power minus X with respect to X, and the value of this integration is root pi by 2. So the expression for P is now gamma root pi by 2 k to the power kt to the power 3 by 2 e to the power minus ef minus ev by kt. Here again this gamma into root pi by 2 gamma root pi by 2 kt to the power 3 by 2 is NV. NV is again effective density of states in valence band. So the expression for P, concentration of holes in valence band, is NV e to the power minus EF minus EV by KT. Now, in case of intrinsic semiconductor, concentration of free electrons in conduction band is same as the concentration of holes in valence band, and that is equal to intrinsic concentration. Now we have the expression for N, that is Nc e to the power minus Ec minus Ef by KT, and P is Nv e to the power minus Ef minus Ev by KT. So in case of intrinsic semiconductor, N and P both are same. So now we can equate the two expressions. For intrinsic semiconductor, this Nc is same as Nv. So now equating 1 and 2, this will give Nc and Nv are same for intrinsic semiconductor. So we have now Ec minus Ef is Ef minus Ev. So Ef is Ec plus Ev divided by 2, and this Ec plus Ev by 2 is Ei, intrinsic energy level. Ei is intrinsic energy level. So for intrinsic semiconductor, Fermi energy level coincides with intrinsic energy level, and intrinsic energy level lies between or at the center of conduction and valence band. This is conduction band and this one is valence band. Intrinsic energy level lies at the center of conduction and valence band, and in case of intrinsic semiconductor, Fermi energy level coincides with intrinsic energy level.